So, hello again, good evening, good afternoon, good day, good morning, good evening, wherever you are in the world.
Hello.
And I'm just logging in. CJ is our student today. Hi, CJ.
Hi.
Good afternoon. How are you today?
Sorry.
How are you today?
I'm good. How are you?
Right, great. I'm doing good, thanks. Okay, we'll continue from where we left off last time, which was,
Wait, can we do 2.3 and 2.4 today?
yeah, okay. 2.3,
For paper one
2.4.
practice.
2.3, 2.4 would be, what was that? That's energy and then that's momentum, right?
Yes.
Okay, so hold on. I'll just change the information on the stream. All right, give me a moment. Momentum and energy. Okay. So while I'm updating this, can you tell me like what exactly is it that you need help with here?
Sorry.
What exactly do you need help with?
Like paper one questions practice.
Okay. Okay, hold on. All right. So paper practice. Okay. You have the questions with you that you'd like to work with? Rather work on.
I don't have questions with you.
All right, hold on. Uh, okay, so while we're waiting, here's the Jamboard link.
Thank you.
Okay, let's work on. Okay, hold on. Give me a moment. I'm gonna try to access some questions. Okay, let's go straight to like problem solving here. So that's gonna be your paper two. Okay, which one should I open?
So with paper one, okay.
All right, you want to do paper one? That's fine as well.
Yeah, because I have like a quiz and it's only on paper one.
Okay, so in that case, sure, we'll do paper one. Hold on, give me a few moments. Let me get some questions. Okay. Um, energy and momentum. Let's look for. Okay. So here's one. I have here a few questions. So we can go through these. Yeah. Okay. So let me. Okay. Here. You have the Jamboard link with you. Can you see the board now? By the way, not yet. All right. Let's go to that.
Yeah, not yet.
All right. This is done. Okay. So let me just update this last bit. All right. So while we're doing this, um, okay. So the key idea first is whenever you have any sort of motion, I actually just discussed this with my class like a few days ago. Yeah. Um,
Mhm.
whenever you see any sort of motion problem, there are there's a particular order you would like to think of. Okay.
Mhm.
Okay, the first thing that you'd think of is you always think of try to solve that particular problem with energy, conservation of energy first. Okay,
Okay.
okay. So the second part, okay, so let me just put this in here. So order of um order of topics to try. Okay, you always try first, and for the most part, try energy first. Specifically, you use conservation of energy. Okay. Now, a lot of these other problems, like find the kinetic energy, find the potential energy, a lot of those other problems are pretty straightforward once you know the formulas, right? But in some problems
Right.
wherein you're really looking at the motion to try when, okay, I'll add that, when solving problems involving the motion, right? Okay. Um, this doesn't mean that you'll always end up using energy, okay? But from what I see, both from my experience and from what I see from other students, a lot of the time it's a lot easier to start with energy. If you cannot solve it with energy, then that's when you use Newton's laws. Okay, all right. And then if you cannot easily use Newton's laws, that's when you go to conservation of momentum. Um, all right. So this is the tip here. So let's just do a quick recap again. I'm just gonna provide you a copy of the data booklets information. Where is the data? Okay. For this one, 2.3 and 2.4, the relevant data, it would be, just copy the whole part of that table here. Okay, so that's a data booklet. Hopefully we can see that. Okay, there we go. Okay. So these are the things that we need to know. Now, for the most part, what you will use in most problems is either this, this, and this. Okay, this and these are related, so whatever form you use, it's going to be the same. Okay.
Mm-hmm.
However, if the problem starts with momentum, then you use this form of kinetic energy. Okay. Otherwise, you're
Wait,
going
the
to,
momentum what?
sorry, say that again.
Sorry, I didn't hear what you said about the equation on 2.4.
All right. So this is what you use. You use this particular formula if momentum is given.
Okay.
Is given. Now, if V is given, you use this. Use if V is given. Okay, because in both cases you will need the mass, right?
Yes.
Okay. All right. So use if. Okay. All right. And then what do we normally use in the formula booklet for work, energy, and power formulas? You will normally use this. Of course, we've known this since the beginning. This is for springs. Okay.
Mm-hmm.
And then we also know this since, I don't know, grade 7 or grade 8 or maybe grade 9, right? Now, this is useful for engine problems. Whenever you see an engine in the problem, you use that formula. Okay.
Mm-hmm.
And of course, finally, efficiency. This is useful in many topics. So I'll just put it here. Useful for other topics as well. Okay. You usually see this in topic 8 and topic 3 and maybe topic 5. Usually. Okay.
Mm-hmm.
All right. All right, so with this in mind, we will be again referring back to this later. Since you do have access, if you need to go back, just go back to this. But I will copy and paste this every so often. Okay?
Okay.
All right. So let's go straight to the point. Let's get practice.
Hey, Mr. Dennis, hey, your microphone's like maxing out, or the audio bitrate is weird.
Hold on, adjusting my mic. All right. How does that sound?
I think it's good right now.
Okay. All right. Good. Uh, so let's continue. Hmm. All right, here's the first problem that I've seen in a past paper that would, um, I think would be already challenging. Okay, this is gonna be already challenging.
Mm.
Okay, before you solve this, I'm gonna give you a clue. Okay, so the hint here is that momentum is a vector while energy is a scalar. Okay, in other words, you need to take into account directions when you add or subtract. Okay,
Mm.
all right. So with this, what's your answer first, and then whether right or wrong, we'll discuss it briefly. Okay.
Okay.
Okay. All right. So what do you think the answer is?
Um. Let me read it again. The wall on the ball
Mm-hmm.
by the wall force exerted by the wall of the ball and the loss of kinetic energy of the ball. So like is it asking when the ball on the wall, what's like the
So
force that happens when it's still there?
yeah.
Okay. Um M?
Okay.
Is it
We don't know the actual mass, so just use m for that, right?
okay, yes.
Okay.
Hmm. Is it either A or B?
It's either A or B. Yes, one of those is correct. Why did you choose either A or B?
Because I thought the speeds would add up.
Mm-hmm. All right. So
Because we're
let.
not trying to look for a change in velocity, right?
Mm-hmm. Mm-hmm.
And is
Actually,
V
we
and
are.
U?
We are.
Oh, okay.
Okay.
Um,
But
is it?
okay, I want to give you something first. Okay, you said velocity. Keep that in mind.
Yeah.
It's not speed. It's velocity. Okay.
Oh, velocity.
Mm-hmm.
Okay. The equation. I don't need the equation right now, right?
Right.
Do I? I think it's the first one.
You think it's A. All right. The correct answer is indeed A. All right. Let's
Because
this.
U squared and right, V squared.
Okay. Yeah, that's correct. So let's kind of look at this. This is easier because of the fact that it's a scalar. You just have to subtract, right? So that's gonna be 1/2 mass uh u squared minus 1/2 mv squared, right? So we factor out the 1/2 m, and you're gonna be left with u squared minus v squared, which is exactly what we have for A, right? So this would also be correct for the loss of kinetic energy. Now, why is it not C? Okay, in order to do this much more clearly, remember the first step in solving any physics question. Draw a diagram of the situation, right? Okay, so if this were your wall, you have a ball, it's moving this way with you, and then it bounces off with the speed v, right? Remember that this v should be negative because it's going to the other side. It's pointing to the left when it's pointing to the right. So in this case, you were right. You have to find a difference in momentum. So you have to do mu minus m times negative v. Why negative again for v? It's going the opposite way. So this becomes, then don't forget over t, because that's how you find the force, right?
Mm-hmm.
So, all right, so let's just start that from the beginning. So change in the momentum over t, that's equal to the force, and then momentum is mv.
Right.
So So what are we going to be left with? So we're left with mu minus m times negative v all over t. Oops. So mu minus m times negative v all over t. We're left with, well, it uses capital T here, so we'll use that. So that will be equal to, force is equal to that, and that's going to be equal to m times u plus v all over t. And that's why the answer is A. Okay. So
Okay.
let's just put that in there again. Always use directions with momentum. Always use directions with momentum, and thus the the appropriate signs or minus signs. Okay.
Always use.
Again, always use directions on with momentum.
Yeah. Okay.
And thus you always use the appropriate plus or minus signs. All right. Okay. For energy, you don't have to do that. Uh, so I'll just put this here with energy. Um, the change in energy is a simple subtraction problem.
Mhm.
Okay. Right. Is that clear now? How to do that kind of problem? Okay.
Yes.
Clearish, clearish. All right. So I'm gonna
Okay.
look for another momentum problem similar to that. Okay. This one is a bit different. It's similar enough, but I think it's a little bit more
I think
challenging
it's
because of
yeah.
it's a little bit more challenging because of some additional information.
Hmm.
Okay, there. What is the change in the momentum of the ball?
Uh oh.
Okay, so the ball rebounds at the same speed and the same angle.
Wait. So it rebounds, and then when it rebounds again, it's the same speed.
Mm-hmm. So basically,
Um.
it goes in here. Let's put a number to it. Let's say 10 meters per second. It goes like that, 10 meters per second as well.
Mhm. Wouldn't it be zero?
Again, I'm gonna point this out. Momentum is a vector.
Oh. Um. The vector. So is it one of the sine cosine ones?
Mm-hmm. Okay, it's either one of those. Why do you eliminate C?
Because it goes in a direction,
Mm-hmm.
and cosine and sine's one of the axes.
Okay, great.
Is cosine in this case the x?
Mm-hmm. Correct.
So I think the x changes a
Okay.
lot.
Okay, right.
So
So is it
B.
A or B? Okay.
B.
Right. Your answer is B, and that is the correct answer. Okay. So just quick discussion again on why this is the case. Yeah. So let's take a look here. It says here if you want to be a bit more technical with it with the math. So what happens here is you have two components. This is Vy going in this way, right? And
Mhm.
Vx going in this way here, Vx, right? And then on the rebound, it's gonna go this way now. This is now negative Vx, right? But it's still Vy. So the change in the momentum, so change in the momentum is happening only on the x-axis, as you mentioned, right?
Mhm.
Only along x. Okay. So all we have to do now is determine what Vx is. So Vx, as you said, that should be equal to V cosine theta. So the change in the momentum will be equal to negative Vx minus negative Vx times the mass. Okay, so that's gonna be 2mvx, and then that's gonna be 2mv cosine theta, hence B. All right. The shorter reasoning here is exactly what you said. The change in the momentum only happens in the x direction, so it must be either sine or cosine. Then looking at the angles, it must be cosine. B.
Mhm.
Okay. So all right. So that's good. Actually, what you're doing, I just want to point this out now. Okay. It's a very good idea to reason out a lot of these things rather than solve them. Okay. In IB physics paper 1, the MCQ section, okay, it is always faster to reason out the answer than to solve it. Than to solve it. So keep that in mind whenever you're um, solving these kinds of problems. For MCQ only. Of course, when it comes to paper 2 and paper 3, you really have to solve because you have to show the working, right?
Yeah.
Okay. So here's the next problem. Okay. Again, it's still based on momentum. So we're gonna do momentum for like the first half. Okay.
Okay.
All right. Here we go. Um, there. The objects collide and stick together. What is
Mm.
the total
Mhm.
change in the linear momentum of the objects as a result of the collision?
Um, they add.
Mm-hmm.
No, they add because like I feel like when you like hit something,
Mm-hmm.
gets momentum. But if
Uh-huh.
they both hit each other, they both get momentum.
Uh-huh. All right. So what's your answer?
But if they stick together,
Mm-hmm.
change of linear momentum.
Hmm. This is an interesting win.
I feel like it would add up if it bounces back, but
Uh-huh.
if it just sticks together, I feel like it subtracts.
Mm-hmm.
So I would say uh C M2 or like
See.
the 2 minus the 1.
Okay. Correct answer here is D.
Okay.
Okay. Why? Here's the. I'll give you a hint first. Okay. If there is only one object in a momentum problem, okay, object in a momentum problem, you use um, the P uh, or F formulas. Okay. So in other words, bless you. In other words, you're gonna use P equals mv or F equals change in momentum over time, right? But
Mhm.
if there are multiple objects, two or more, most of the time they're two, right? Most uh, most of the time, two objects, right? But whether you have one, two, three, four, five, six, no matter how many objects you have, okay? If there are
Mhm.
multiple objects, go straight to the idea, straight to the idea of conservation of momentum. Okay. Now, what does that mean? I'll just put this here first. Okay. Mhm. Okay, if there are multiple objects, you go straight to conservation of momentum. What does conservation of momentum here mean? The sum of the initial momentum should be equal to the sum of the final momentum. That's one way of saying it, and this is the way that you would normally see it. Okay, now, um, so basically, this question is asking the momentum here at this is the before, this is the I, right?
Mm-hmm.
So the momentum here should be equal to m1 v1 minus m2 v2, right? That's the that's the total momentum, m2 v2. So which kind of makes you tempted to do C or maybe B, right?
Mm-hmm.
But thing again is it's asking for the total change. Remember, they are equal. So in other words, total momentum does not change. Again, the total momentum of I'll add this here of a system of a closed system doesn't change. A closed system, I think you should be familiar with that. But in case you're not, closed system basically is a system wherein there are no forces, no external forces acting on it. It's just the two objects interacting. Okay.
Mm-hmm.
All right. So in this case, the question again is about the total change in the linear momentum of the two objects. So the answer is zero because the total momentum shouldn't change. Okay. Um, the individual momentums could change. The individual values for the momentum of each object should may change, but the actual total doesn't. Okay.
Yeah.
All right. Does that make sense to you? If it doesn't
And
quite, it's fine because a lot of students still kind of like try to grasp the idea a lot of the time here.
wait, so if it's one object and hits a wall and bounces back, the
Mm-hmm.
momentum doesn't change either.
The momentum of the object and the wall doesn't change.
Okay.
Okay, but if you're looking only at the ball, so let's go back to that problem since you asked, right?
Mm-hmm.
Uh, Basically, it's this one, right?
Mm-hmm.
In this case, the ball's momentum changes, ball speed changes, right? And then the wall's momentum should also change, also changes. Most of the time, though, you don't see that change because the wall is much more massive than the ball, right?
Mm-hmm.
Okay, but it does change. However, um, the two changes cancel out. Changes cancel out. Okay, so basically, one another way of thinking about it is the wall bounces back, but the wall kind of like gets pushed back. Then afterwards, it vibrates,
Mm-hmm.
right? So the vibration is caused by the wall moving back because of the collision, and then once it goes back, it reaches the limit of it going back, and then it starts to vibrate. So again, if you do it like this is the ball. As the ball bounces, this kind of does that.
Does that mean the momentum is changing while it's doing that?
Yes, the momentum of the wall changed after the collision.
Mm-hmm.
But again, the two changes will cancel each other out. So the overall change in momentum in the system is zero.
Okay.
All right.
So two objects still cancel each other out.
Yeah. Whenever you see two objects, if the problem is about two objects, the changes cancel out.
Mm-hmm. Okay.
Okay. If the question is only about one object, then it doesn't. You just have to solve it normally. Okay.
Mm-hmm.
All right. Hey. Um. Let's take a look at another problem. Okay. Momentum. That's force. That's force. Work done. Energy. Okay. This is gonna be a combination of both energy and momentum. Okay, here's the next question. What must be true about the total momentum of the two bodies and the total kinetic energy during the interaction? Hmm.
Mm, but is kinetic energy conserved? I don't think so.
Uh, Total energy is conserved, but just like momentum, the momentum of a single object doesn't it can change, right? So
Yeah.
same thing, kinetic energy can change, potential energy can change, but total energy closed system doesn't change. So that's the good question though. It does say kinetic, right?
Mhm. Wait, so is it A? Because of what you've been telling me,
Mm-hmm.
the momentum, the change in momentum is zero after the two objects collide.
Mm-hmm.
So momentum should be conserved.
Okay, correct. This is the correct answer. Okay.
Okay. Wait.
Okay. A very good example here. This is inelastic, right? Um, the key idea here is only in uh, totally or perfectly elastic collisions. It's gonna be the better word. Only in perfectly elastic collisions, elastic collisions is kinetic energy conserved. Okay, so that's it. Now, a good example here is this: if you have, um, what if you have two rubber balls, right? Now you know that this would be moving at the speed v, for example, u1, and then it's gonna go at the speed u2, right? So what would
Mhm.
happen when they bounce off? So when they bounce off each other, this is gonna go at some speed v1, and this is gonna go off at some speed v2, right? Okay. Now the easy way to think about this is, since no energy is lost, uh, since this is elastic, so no energy lost, right? Energy lost. So in other words, the kinetic energy here, just like Ke1, the sum of that, and then the sum of the kinetic energy here, they should be equal. Okay. So again, if it's elastic, no energy loss, so um, change in Ke1 should be equal to the change in the Ke2. Okay. Or the sum, not the change. The sum. The sum of the kinetic energies of both these objects must be the same. Okay.
Mhm.
Um, all right, let's just do the other one real quickly. If you have two objects, now this time instead of having two rubber balls, let's say that this is a steel ball, okay, and this is a magnet, okay. So they're coming together like that, and then eventually, when they so u1, u2, and then let's say they stick together because that's what happens if one is a magnet, one is steel, right? So let's just say that it goes here at a speed v2 or v1, and they're moving together, right? Now think about it this way. Actually no, let's not even think of it this way. Let's say that in this particular case, they have equal masses, mass 1, and this is mass, right?
Mhm.
Have you ever seen like two objects of the same mass collide with each other and then stick? What happens?
Magnets,
Okay. And what happens? Do they continue moving in either direction, or do they, like, when they combine together they stop?
when they combine, they just flip over.
Okay, they just flip over and stop, right? So let's say that this is V. let's just say that's u. Just make everything equal. So just do um, u and u, just to really emphasize the point, right? So here the momentum here is mu. The momentum of this other guy is negative mu, right? So what's the sum of the momentum here? Mu plus negative mu gives you 0,
And yeah.
right? So that means here the momentum must also be equal to 0,
Zero.
right? But that's
Yeah.
going to be 2m times whatever the speed is. So this implies that v equals 0 because the mass cannot be 0, right? Okay, so in this case, the kinetic energy here has some value, but the kinetic energy here is equal to 0. So you can see that for inelastic collisions, this doesn't have to be all types of sorry, this doesn't have to be perfectly inelastic. All types of non-perfect collisions are inelastic.
Mm-hmm.
Okay, for any inelastic collisions, Ke is not conserved. Where does the energy go? Conserved. Okay, where does the energy go? Um, it goes into the idea of them sticking together. So it could be like it could be turned into some elastic energy because it compresses something, or it deforms the
Right.
stuff. It could turn to
Right.
thermal energy because it vibrates, right? Or
Mm-hmm.
it could turn to, I don't know. Those would be the two most common ones. Either thermal because of vibrations due to the collision, or deformation, so elastic energy. Okay. All
Yeah.
right. So that's why the answer. Let's go back here. That's why the answer here is A, which you got right. Okay. So momentum.
Sorry.
Okay. Okay. I'll give you one more momentum problem, and then let's move on to energy.
Sure.
Yeah. So there's a good momentum problem on this one. And okay. This is something that you must know. There is usually a graph problem about um yeah, there's usually a graph problem like this. Okay. I'm gonna give you a
Okay.
clue here. Okay. The clue here is when you see a graph. Okay. Um, this is you can get the impulse here. Are you familiar with this term, or at least do you remember this term?
I've seen it, but I don't know it.
Okay, impulse. Let's go back to the data booklet first. Where's the data booklet? Okay, here. I'll just copy this. Then okay, here. Okay. Um, let's make it smaller. Okay, impulse is actually mentioned right there. That's the last equation on 2.4, right?
Mm-hmm.
Okay, so impulse is defined either as force times force times the time taken, or the change in the momentum. So you can just write that. I'm just gonna write that F delta T equals delta P, right? Okay. So why do we need this? We actually most of the time need this particular side of the relationship. We don't normally see this word being used, but it's worth knowing, right? It's worth knowing. So in this case, um, okay. So what does this mean? This basically means that if your force is constant, there are two possible applications. Okay. If F is constant, then use straight away, right?
Mm-hmm.
Okay. The other one is if the force isn't constant, F not constant, right? Then change in momentum. is equal to the area under the graph. And this is what you need here for this problem. This idea that the change in the momentum is the area under the graph. Okay, this is the more relevant one for us. Okay, so what's force max?
Force max
Mm-hmm.
is wherever 420 seconds happens.
Mm-hmm. Okay, so that's that. Yeah, that's true. So this is okay. I'm gonna show you how to solve this one now because you're not that familiar with it yet, right? But
Yeah.
this is gonna be basically, you know that this is 420, right? Wrong one.
Mhm.
420. All right. Thing though is we don't need to know that that's 420. In fact, as long as it what you do here is that this area here is your change in momentum. Okay. Um, what is F max? Okay. Just before impact, ball is traveling horizontally at speed of 4 meters per second, and then it says sticks to it, right? So what's gonna happen here? This change in momentum is gonna be m times 4 minus 0 meters per second. Okay, and this mass here, that's 0.2 kilograms. Okay, so if we put that into the yeah, well, never mind, this is no calculator because this is paper one, so you just multiply that. That's gonna give us 0.8, right? So change in momentum is equal to 0.8, and this should be equal to the area under the curve, area, and you see that's a triangle. So I'm gonna write 1/2 times 40. Sorry, F max first. I don't have space. Let's redo that. Okay, so the area, that's gonna be a triangle. So I'll just write it here. 0.8 is equal to 1/2 F max, because that's what we're looking for, times this, the difference here. That's gonna be 40, right? But the time is in microseconds or milliseconds, so we have to put times 10 to the minus 3 seconds. Okay, then finally from here we get F max is equal to 1.6 divided by 40 times 10 to the minus 3. That should give us something along the lines of either B or D just by looking at it, right? That's basically
Mhm.
16 divided by 4, right? So what's that gonna be? That's gonna be 0, 10 to the 3. Okay, so let's just finalize the calculation. So there, we now have 1.6 divided by 4 times 10 to the minus 2. And that's gonna give us 1.6 over 4 times 10 squared. So that's gonna give us 0.4 times 100. And which one is gonna be? So it's gonna be D. Final answer is D. So this is wrong. D.
Okay, wait. So you
Okay.
do P equals mv or delta
Yes.
P equals mv, and then you use impulse, but you rearranged it so it's P equals F delta T.
Mm-hmm. Right. Correct.
Okay.
Correct. And then you,
But I don't know why it's 10 to the negative 3.
why is it 10 to the negative 3? Because our unit here is milliseconds.
Oh, okay.
Okay.
But then it's 1/2 F max,
Again,
half F.
so the other important part is this, okay? If the force is not constant, in this case the force is changing,
Oh, right. It's
then
like
you
a
use the
triangle.
area. Mhm. Use the area of the graph.
Hmm.
Okay. If the force is constant, just use the equation straight away. Make
Right.
this one. Okay. All right. Is that clear?
Yes.
All right. Now let's go on to energy because I want you to be able to do that briefly. Okay, so let's go back. Let me look for. Oh, okay. This one's interesting. This one's about energy. Okay, so you have a graph. Um, okay. So again, we're looking at the graph. Let me make that bigger. There. Okay, I'll give you a clue here. Okay, so for a what's this? For a force x displacement graph. Okay, for a force displacement graph, work done is equal to area under graph. So basically the same as earlier, same idea. Okay,
Mm.
all right. But the thing is, you're not given a force graph. You're not given a force displacement graph. You're given an acceleration displacement graph.
Displacement.
Mhm. So how do you change that acceleration into force?
Um, multiply by mass.
Multiply by the mass, correct. So times m equals force, right?
Yeah.
Okay. All right. So from there, use these two ideas. What's the total work done on the object?
Um. Oh, does that mean I keep adding? No, work is the equation. What's the equation?
What's the equation? Again, use this.
Force displacement cosine theta.
Use this.
Yeah, area. Do I? Okay, so I find the area of this rectangle and the triangle.
Correct.
So 15 times 60.
So
Ooh,
this, and then so what's that area and what's this area?
is the green area 900?
20 times. No, not. Oh, wait. It is 900. For
Okay,
if you use the force version already, right? So
yeah,
this is gonna be 900. Oops. This is 900.
900. And the other
Okay.
one is 10 times 6, 600.
600. Correct. So you already know the answer.
1500 D.
Okay. So also because of the times 3, this is gonna be 60, right? So there. So D
Mm.
correct. All right. Next one. That's not. I'm looking for energy. Okay. Okay. Hold on. This one. What's the power developed by the student given this information? Right there.
Um, power. Okay, so work, useful work done over time.
Mm-hmm.
Uh, F S S is 6. F is um I don't know how to use time in this.
Okay. Okay. So go back. Definition of power. That's gonna be
Oh, over time. Oh, very good.
change in energy over time or equal to work done over time. Right.
Yeah. Um, then it is FS. So it's just 600 times 6.
Mm-hmm.
So it's like 2400. Wait, no, it's 3600.
Mm-hmm.
3,600 divided by 8. So,
Okay, correct.
is that wrong?
Yeah, you're correct. You're correct.
Okay. Um, it's like 450 D.
Okay. So, all right. So you have D. That's I'll just calculate that now. So again, work done, as you said, this will be equal to 600. Work done is equal to force times distance, right? Our
Mm-hmm.
force, our minimum force is 600 newtons, and then the distance is 6 meters, right? So that's gonna be 3,600 joules. Then power is equal to 3,600 joules divided by 8.0 seconds. Let's just do canceling out. This is 1800, then 4. Still can cancel out. We're left with 900 over 2. And finally, 900 over 2 is 450 watts. So it is correct. Okay. Um, all right. Next, we'll extend like maybe 5 to 10 minutes. According to
Okay.
Preply time. Yeah.
Okay.
All right. Where's an easy one? Okay. This one's difficult, so I'll skip to that. I'll go back to that later. Projectile, tennis ball. Oh, okay. This one is. Okay, this one is a little bit tricky, but should be doable. Easily doable. Okay, so you have an object that has an initial kinetic energy of 48 joules, and then you have a constant frictional force that brings it to rest over 2 meters. What's the frictional force on the block?
Mm, okay. Frictional force. Let's see. So we use work equals Fs.
Correct.
So rearrange it so that um, F is isolated.
Mm-hmm.
So that means 48 divided by 2, 24.
Okay, so your answer is A.
Hey.
Correct. Okay, correct. Um, okay. Just want to make sure for those listening into the stream later and for you as well. Okay. Remember that this work done is always for an individual force. Okay, individual force. Okay. So this means this force is referring to that F. Okay.
Mm-hmm.
All right. Now, if you have several forces, then you can actually do find the work done by each of those forces and then add them up depending on the situation. Okay. All right. Great. Let's do another one. Oh, okay. This one should be easy. Number. Okay. Okay. There. Okay. The efficiency is 20%. Then you waste 500 joules. So what was the useful work done?
Okay, so we use the last equation of
Mm-hmm.
the 2.3
Mm-hmm.
efficiency. So 20%
Mm-hmm.
equals uh, wasted.
Uh-huh.
So the top is like work minus 500.
Okay. So this is the okay. So the total work done. So okay, 20% is equal to. Oh, I'll start with the equation. Hold on. So we start off, as you said, with the equation. You do efficiency equals useful out over total in, right?
Mm-hmm.
Okay. What's the useful out? We don't know. But you said some value x minus 500, right?
Yeah.
This is 20%, so 0.2. Then total in should be x, right?
Mm-hmm.
Okay. Then find x. This is, however, I'm gonna say this is, I think this is gonna take a bit longer than what you would like to do. But okay.
Yeah.
All right. Uh, okay. Let's continue this. What would we get? So we cross multiply, or we put that x on the other side, right?
Mm-hmm.
Okay. So what are we gonna get? 0.2x.
Equals x
X
minus
minus
500.
500. All right. Correct. Then
Oh,
shift stuff around. We get 500
500
equals, let's just
was.
0 point what x? That's 1 minus 0 0.2, 0 0.8, right?
Mm-hmm.
And then finally, x
Divide
is,
by 0.8.
yeah, 500 over 0 0.8
I think it's 400 D.
d. Okay. All right. So I'm gonna show you. Okay. Mm, okay. All right. Let me just double check your work. Total in. Okay. Okay. 0.2x. Okay. 500. Okay. I'm gonna kind of cheat here now. Let's use a calculator to check that. That's 500 over zero point 0.8. That should give us 625. So our answer's not in the choices, right? Okay,
Oh,
I'm gonna say this much. Your approach is correct. There's something wrong with this, with just the
I
way we
thought it
put
was
the
like
numbers in.
0.8% of, or like 80% of 500. That's what I thought.
Okay. All right. I'm gonna solve this in a slightly different way. Okay. But again, I'm gonna use the logic bit first before I actually solve. Okay. Um,
Mm-hmm.
okay. The reason what I'm gonna do here is I'm gonna think that the energy that 500 joules is wasted, and this is the 80%, right?
Mm-hmm.
Okay. So what I'm gonna do is I'm gonna look for, okay, I'm gonna look for, I'm gonna divide this by 4, and I'm also gonna divide this by 4. Why? Because this is gonna give me my 20%, right? And this is gonna be 125 joules. And this is the, why did I want it to be 20% here? Because we know that the 20% is the useful work, right? So there's our answer. The answer is B. Okay.
Mm-hmm.
All right. Okay. I'm gonna see what went wrong with the original solution, but I think the original solution should have worked. Maybe we just did something wrong with the math. Okay. So the correct answer here is B, but your reasoning is correct. I just want to see where we went wrong later. Okay. All right. Let's do one last problem. Let's look for a hard one. Not that. Uh, I've done that. We've done that, so that's not it. Okay, this last one here. Uh, okay, last one for today. Okay, so you have a train on a horizontal straight track moving from rest at constant acceleration. Keep that in mind, constant acceleration. Horizontal forces on the plane on the train are the engine force and the resistive force, but that resistive force increases with speed. So which graph represents a variation of the power developed by the engine? Now to help you out, I'm just gonna go back to the data booklet. What's gonna be the formula to use? I'm gonna put the formula right away here. So that's the formula to use. Power equals FV. Okay. I just want to label this. This power should be the power of the engine. This is not
Mm-hmm.
the overall power. Okay. This also means that this F is the driving force. Okay. All right. This one's difficult. I'm going to tell you that. So I'll just tell you the answer if you don't know. Then we'll go through how to do it.
Power equals force times velocity.
Mm-hmm.
Okay. Um, is it exponential? No, it's not. It's not. It's not.
No, no, it's not quite.
B.
Your answer is B. The correct answer is D.
Okay.
Okay, I'll explain now, yeah? So the reason
It looks like.
here, okay, the reason here is this, we start with that, constant acceleration. So that means the sum of the forces equals, divided by the mass, should be equal to the acceleration, and this is constant, right?
Mm-hmm.
Okay, so because of that, because of this fact here, what's going to be the sum of the forces on the train? Whoops. The sum of the forces on the train are the driving force, FD. I'll just say F, right? Um, F, then resistive force minus R. I'm just going to write that as R, okay? Then over M is equal to a constant. But the mass is a constant as well. If we put that in there as well, then that means F minus R is a constant, right?
Mm-hmm.
Okay, so, um, okay, let's go to the next page just so we can finish it. So F minus R is a constant. Then that means the F is equal to some constant. Now, it's also mentioned that R varies with speed, right? So if we write that in equation form, R is equal to some constant as well, plus, times V, right? So I'm going to write that plus kV, and I'm going to write this constant now as C. Okay, so this one you really need to do math in this part, C plus kV, right? But you know that from here, power equals FV. So from here, force should be equal to the power over V, right? And
Mm-hmm.
then from here, we do power over V is equal to C plus kV. And then we move this V to the other side. We get power is equal to CV plus kV squared. In other words, you get a quadratic formula for power. Quadratic formula for power, right? For power, um, versus V, right? So for your choices, which one is a quadratic? D.
Uh, B.
This is quadratic, as this is exponential, right?
Mm-hmm.
Exponential. Okay, this is linear. This is no relationship, right?
Yeah.
Okay, so automatically A would be wrong, okay, because of the fact that we need constant acceleration. Okay, uh like I said, this is the most difficult of the problems that I'm giving to you because of the fact that this has no other solution except the mathematical one. You
Right.
cannot reason this out easily. Okay,
Mm-hmm.
all right, so we'll end here. If you do have some problems you have access to, just go ahead and do them. And of course, as you want to do, as if you have any questions about them, just send me a message here. If I can reply, I'll reply. Right. All right, so any other questions before we end for today, CJ?
This question is hard.
Yeah, this particular question is hard. I gave this to my SL students as well. No one got this question. They all,
Yeah.
most of them answered C.
Yeah.
All right. Okay. So with that, yeah, difficult questions, send them over. If you can't send over the problem, just send me over the problem number along with the paper, and
Okay.
then we'll go through it. Yeah.
Sure. Okay.
All right. So
Thank you.
with that, I'll see you next time again, CJ. Good luck with the quiz.
Thank you.
All right. Bye bye now. Have a good evening.
Good evening. Bye.
All right. All right. So that's the end of the class. CJ was actually picking up pretty fast, actually, in my opinion. He just needs a lot of problem. Well, he just needs a lot of practice, I think. So for those who would like to again do these problems, of course, if you'd like help from me, just send me a message, and if it's an easier one for us to do, we can do it on the stream later on. But otherwise, if you need a lot of help, just send me a message through any of these platforms. I personally use Facebook the most, so if you'd like to send me a message over Facebook for help, you can do so. Um, if it's an easy problem, it's okay. I can just do it with you. But if it's really dedicated tutoring, like what I do with the students I have, you can ask me for a personal link or booking individual sessions. Okay. Right now, though, I'm pretty swamped with students and other activities. So once I open up, my schedule opens up, then yeah, I'll be taking in other students. But for now, I'm just taking those few. But if you need help on simple problems, I'm more than willing to give you that. Now, having said that, please don't forget to subscribe and like on the various social media platforms here. Twitter, oh sorry, not Twitter, Twitch. I'm not that active, but I do just stream there just in case somebody's interested. I am actually expecting most subscribers to be on Facebook or YouTube. Then for TikTok and Instagram, I think I can set them up sometime this week. The accounts are already active, but there's no content in them just yet. So, um, yeah, for those two platforms, just wait because content coming up real soon. All right. So we'll end it here as well on the stream. So thank you for listening later on. For those who would like to watch the stream on a later date or those who stumble upon these videos, thank you for watching all the way to the end. I'll see you guys and stay freaky, everyone. Bye for now.